Hello and welcome everybody to our Fronius webinar. Today, we shall be discussing proper Fronius PV system design. So basically, we will be looking at methods and tools we use in Fronius to properly design a PV system. Of course, I won't be doing this alone. I'm here with Byron Kutzer, who is the Technical Sales Advisor for the Southern Africa region. He is based in Johannesburg, South Africa. And then, of course, myself, Cyprian Okolo. I am the Technical Sales Advisor for the Western Africa region. I am based in Lagos, Nigeria. And together, we shall be presenting this webinar today. So let's start up with the agenda. So we're going to look at system design, especially taking a look at the stringing or array orientation. We'll take a bit of a look at the DC cabling and sizing. And then we'll do a bit of a system simulation or design using the Fronius Solar.Creator and Solar.Configurator. And then Byron will come in with the construction part, where he'll be giving you information about layout and installation of PV system. And then will, of course, give us further information afterwards. So without further ado, let's jump into the presentation. But then before we start, please feel free to ask questions during the webinar. We shall, of course, try our possible best to answer them during the webinar. And then if not, we'll, of course, respond to you via email. Your opinion, of course, is very important to us, so please would like to have your feedback on the content of our presentation. So let's get on with it. To start off, let's look at PV system design, where we'll first of all be looking at PV array stringing. So this tends to present a bit of a tricky situation for design engineers and installers. So we'll take our time to explain how this can be done using or with reference relative to a Fronius inverter. Great. So first up, let's look at the PV panel layout. And we'll be taking a look, first of all, at series layout. This, of course, is usually how strings are connected. So for best practice, all modules in series should be of the same type from the same manufacturer. And then it is, of course, important not to mix panels with different short circuit currents in series. An allowable option is that you can mix panels with different voltages in series. So we're going to have a look at this in context. But then we'll have just a statement to summarize what I just mentioned, that the performance of a solar array is as strong as the performance of the weakest element. We're going to find that out in the subsequent slide with illustrations. So let's start up with a series connection of 3 panels, as you can see, all with 400 watts capacity, with operating voltage and current of 40 volts and 10 amps respectively. So the total voltage, since they're connected in series, is going to add up, because the voltage drop across one panel will be added to the voltage drop across the other panels. So it's going to be, in this case, 40 plus 40 plus 40. So that gives us the sum of 120. In terms of the current, the same current that passes through one panel passes through the other panels, so long as they're connected in series. So you're going to have a common current, which is 10 amps, which is also the specification on the respective panels, as you can see. So in this case, the total power will be 120 volts, which is the summation of all the voltages of the respective panels, multiplied by the total current, which is 10 amps. This gives us 1,200 watts or 1.2 kilowatts, which is basically 3 times the capacity of one panel. That is 3 times 400. So in this case, this design is correct. Next up, we're going to look at a similar design, but with a little bit of variation. So in this case, we have two similar panels of 400 watts each, and then a panel that is 200 watts, operating voltage of 20 volts in this case. So the total voltage, as in the first case, is going to sum up. So we have 20 plus 40 plus 40, that gives us 100 volts. And then the total current is just like the previous illustration, the same across series connections, which is 10 amps. So total power will now be 100 volts times 10, which gives us 1 kilowatt or 1,000 watts, which is the same as adding 200 watts plus the multiplication of the two other panels of 400 watts. So this is also fine. Let's now look at the third illustration. In this case, there's a slight difference in the current of one particular panel. The others are the same, 40 volts, 10 amps. But then for this, it's 40 volts and 5 amps. The total voltage in this case will, of course, be the summation of the operating voltages, which is 40 plus 40 plus 40, which gives us 120 volts. But then the total current in this case, because of the amperage of this particular panel, it is only 5 amps that will be allowed to pass through this series connection. So the total current will be 5 amps, as you can see. So the total power will now result to 120 volts times 5. This gives us 600 watts. As you can see, comparing with the other setups, we can see that the total power in this case comes short with about half of the first illustration. And of course, we can see that it's it puts the whole system at a disadvantage in terms of yield power. So this would not be a smart choice to make. So as stated earlier, the total current of a system or of a circuit or of a series connection of panels, otherwise called string, the total current is determined by the panel with the weakest or the lowest current rating when connected in series. Good. So let's continue to let's have parallel layout of panels. So for parallel layout, for best practice, all modules in parallel should be of the same type and from the same manufacturer. Please never mix panels with different open circuit voltages in parallel. An allowable option is that you can mix panels with different currents in parallel. So, in summary, the performance of a solar array is as strong as the performance of the weakest element, just as stated before. So let's now look at illustrations to buttress this fact. First off is a power connection with the same specifications as before. So, but in this case, we have a parallel connection. So for all parallel connections, the voltage drop is the same. So in this case, we're going to have 40 volts as the total voltage. But then in terms of the total current, it's going to be a summation of the current flow through the respective panels, because the current that flows through this panel is different from the current that flows through this panel. That is, if they have different specifications. So basically, to get the total current, the current through the branches have to add up. So that's basically the explanation. So we're going to have 10 plus 10 plus 10. In this case, they're all the same. So they're all added up, and then we'll have the sum of 30 amps. So total power will now be 40 volts times 30 amps. This gives us 1.2 kilowatts, or a multiplication of the three panel capacities. So this is fine. Next up is another variant of the parallel connection. In this case, we have just one difference from the other two panels of 200 watts and 5 amps. So in this case, the currents add up, as you can see. So 5 plus 10 plus 10 gives us 25. And then the voltage across the parallel connections is the same. So they're all the same. So it's 40 volts. So total power is 40 times 25. That gives us 1 kilowatt. This is also fine. So now let's look at the third variation. So in this case, we have a different voltage, operating voltage for a particular panel. The other one's 40, while this one is 20. So in this case, the total voltage, or the voltage across this power connection, will be the voltage of the weakest element here, in this case 20 volts. Total current, by the way, is going to be a summation of all the current flowing through the respective panels. So that gives us 10 plus 10 plus 10, which is 30. And then the total power will be equal to 20 times 30, which is equal to 600. As you can see, falls short of the other illustrations as mentioned earlier. So, of course, this wouldn't be a smart choice to make. So in summary, the total voltage, as earlier said, is determined by the panel with the lowest voltage rating when connected in parallel. So these are design checks we should make while designing the system as an installer. Good. Now let's go to, still on the PV array design, we can actually calculate the number of panels that can be connected as a string to an inverter. So it is given by this particular equation, which reads VDC max of the inverter minus VOC of the module divided by MPP max of the module. So just an explanation of the equation. So VDC max is basically the maximum input voltage of the inverter, otherwise known as the maximum DC voltage that the inverter can handle. Then VOC of the module is basically the open circuit voltage of the module, also known as the voltage output of a single solar panel when it is not connected to the inverter or any load. Now, VMPP max of the module is basically the panel's maximum power point voltage, otherwise known as the voltage at which the solar panel produces maximum power. And this is typically around 80% of the open circuit voltage. So if we want to put this in context, I could give us an example. So verbally, of course. So if we have a VDC max of an inverter of 1000 volts, and then VOC, that is open circuit voltage of this particular module, or the module to be used to be 49.8. Actually took this off the nameplate of a particular module. And then we have its VMPP max to be 41.7. So if we impute these figures into this equation, we're going to have 22.78. So according to the equation, this tells us that for safety, we're going to round it down to 22. So you can connect a maximum of 22 of this panel to an inverter with a maximum input voltage of 1000 volts. So that's basically what this equation means. So with this, it already gives you, as a design engineer or installer, an idea of the maximum number of solar panels or modules that can be connected per string. So to continue, it is important to note that this equation only determines the maximum number of panels that can be connected in series, because we have other factors such as shading, temperature, and panel orientation that have to also be considered when doing your system design. I'm going to be telling us more about panel orientation, I think, in the next slide, of course. So the solar panel orientation, the general rule is that PV systems in the northern hemisphere should have their panels facing due south, and vice versa for systems in the southern hemisphere. And please note that we will be dealing with the geographical points in this case, and not the magnetic points. So in terms of geographic north, we mean, of course, the geographic north and not the magnetic north. They are two different entities. So please take note. So the angle that the solar panel should be set at should be at best perpendicular to the incoming rays of the sun. So that is the condition where the solar panels will generate its maximum power. So meaning that the rays that incident on the surface of the solar panels should be at 90 degrees in order to generate the maximum possible values of solar yield from a particular panel. So in order to achieve this, it now behoves on us that we have to tilt our panels to a particular tilt angle to get this. So that is where the tilt angle comes into play. So a general rule for optimal annual energy production is to set the solar panel tilt angle to the geographical latitude. Okay, so taking, for example, Byron's region, Cape Town, for example, whose coordinates are shown, it is therefore, and of course we know that Cape Town is in Southern Africa, it's in the Southern Hemisphere, so which is why it has -33, because it's on the negative y-axis. So hence, an ideal tilt angle for panels should be 33 degrees due north. And I've taken my location, for example, in Lagos, Nigeria, with latitude of approximately 6 degrees. Of course, we're in the Northern Hemisphere. That should now be the tilt angle that would provide the optimal energy production. But in this case, it should be facing due south. Good. But of course, there are places like Nairobi, Kenya, that has locations that are on the equator, that is at 0 degrees latitude. So these panels in these regions can, of course, be placed horizontally. Good. So continuing, let's have a look at DC cabling. So a bit of information about DC cabling and sizing. The current carrying capacity must be equal to or greater than the current to be carried. This is, of course, very, very important so that we don't overload the cable, because this would, of course, lead to overheating of the cable, and then, of course, will result in lower yield. A good suggestion is to always size it to about 1.25 times of the nominal current, or you can even go above up to 1.5 times. The cable must be able to withstand harsh environmental conditions. Special attention needs to be paid to the voltage drop, because this increases with respect to the cable length. And then also to be considered is the orientation of the cables, either it's going to be stranded or solid core. But it's good to note here that stranded cables have more current carrying capacity than solid core cables. And then, of course, finally, we need to consider the specific resistance of the cables to be used, either of course, the material of the cable to be used, if it's copper or aluminum, because they have different specific resistance, as we can see here. So, and then just to add some bit of context to it, you can have, here we have the different gauges and what these gauges of cables can be used for. Also, in addition, there is what we call acceptable loss for a particular system, because so long as you're using cables and they're going a particular distance, there's going to be voltage drop across the length of the cable. So there are softwares you can use to calculate this. All you need to do is to impute the necessary data, and then it will come up with the acceptable loss. Usually it's best to be in the region of 1 to 2%. And then for this particular cable, for this particular equation or software, it gives you the cable size required to run the installation of this particular data being imputed here. Good. So let's now go to system simulation. Now, how can we use Fronius tools to actually design a system. So we'll be looking at the tools that we can use, tools provided by Fronius to be used for system design. First up is the Solar.Creator. I'm going to be doing, say, an abridged explanation or presentation for Solar.Creator because we have dedicated webinars for Solar.Creator and Solar.Configurator. So basically, the Solar.Creator is a user-friendly tool that can be used to have a fully comprehensive design of and simulation of photovoltaic systems in combination with electrical loads or battery systems. And of course, electrical vehicles. We can also use it to select modules for a particular system design. And then it can, of course, generate reports amongst other several features. We're going to be seeing them because I will be doing a demo after a few slides. So next up is the Fronius Solar Configurator. Now, the Fronius Solar Configurator, as we will see subsequently, is a tool that we can use to properly size the strings connected to a particular inverter. Okay, so we can use it to size up the strings connected to a particular inverter. So once that is achieved, we can now translate that to a combination of these strings or of these inverters in a whole system. That is, we can have multiple inverters in a system. So the Fronius configurator is an inverter-based configuration, while the Solar.Creator is a system-based configuration tool. So, like I said, for the Solar configurator, you can use it to design the strings connected to a particular inverter by, of course, selecting the, So first off to note here is that it is now integrated in the Solar.Creator. It is no longer a separate entity or a separate tool. It is now integrated in the Solar.Creator, which makes it, of course, easy to locate and make use of. So for the Solar configurator, we can, of course, select the PV module characteristics. As you can see, the specifications of the module. And then the inverter choice can be made here, of course. And then we can now have other general settings, like if you have a special name for the project or for the installation, if it's going to come with or without storage, you can have an idea about the annual power consumption, and then the load profile can also be imputed. So once this is done, it will be able to give you the possible connection of strings of inverter to be connected to, strings of modules to be connected to the inverter. As you can see, it is going to present a tabular list of all the possibilities. So here, as we could see in the previous slide, we already have a preset value of 34 modules on MPP1 and then 26 on MPPT2, as you can see. So this doesn't mean, so that you don't get it confused. So this doesn't mean that we're connecting 34 inverters to a particular string. This is basically what is going to the MPPT, okay? So as we would see in the explanation in the slide here, so it tells us that that 34 actually is a combination of two strings of modules. So each string carrying 17 modules, as you can see. That is for MPPT1. And then for MPPT2, we're going to have two strings carrying 13 modules each. Okay, so that's how this is done. So with this, you already have the system configuration of the strings to be connected to a particular inverter. In this case is a Fronius Simo 20. So if you want to have more information about this particular choice, you can click on it. Once you click on it, it should, of course, if we select this, once you click on it, it should, this is of course a screenshot. So once you click on it, it's going to give you all the necessary details about this particular configuration. We're going to see that during the demo. Good. So for possible module connection and orientation, it's going to look like this. So referring to the previous selection, so we're going to have two strings of 17 modules each. So we have 17 modules here connected to MPPT1, and then another 17 modules connected to the same MPPT1. Of course, different inputs, but all connected to the same MPPT. So continuing, we're going to have two strings of 13 modules each connected to MPPT2. Now, to make it a bit more clearer, I'm going to see if I can shed more light on it. So what I mean is, so taking this, for example, this is the DC connection point for the SIMO 20. So we can see that we have 6 connection terminals here. Now, please note that the first 3 is the terminals are connected to MPPT1, while these other 3 connected to MPPT2. Okay, these are the negative terminals, as you can see represented by the minus sign. So they're all interconnected. Okay, so but then the first 3 in this case for the positive is for MPPT1, while these other 3 terminals are for MPPT2. What we found out that installers normally do is, for this particular reference that we've made, we found out that we have 4 strings to be connected, right? Yes. So what we find out that installers normally do is that they end up connecting it straight up. So you end up having 3 strings connected to MPPT1 and then 1 string to MPPT2. So the best practice would be to connect 2 strings, that is 1 string here, another string here. Then for MPPT2, you can now jump to the next MPPT, connect 1 here, and then another 1 here. And then their respective negative cables will now come here respectively without any specific order. So once you do this, you're going to ensure, especially in the case where we have east-west orientation, we're going to ensure that we have proper coverage of the daily energy production. Because as we all know, the sun rises from the east and sets in the west. So if the first array connected to MPPT1 is due east, so it's going to generate more energy from sunrise to say noon, and then from noontime to sunset, more energy will be generated from the panels connected on MPPT2, that is due west. So once we do this, we're going to maximize the solar yield production. I hope I have passed on a very important point to all of us. Okay, so going forward, same thing can happen for a Tauro. So we can have something like this, 4 strings of 17 modules, each connected directly for a direct connection to MPPT1 or input 1, and then same thing for input 2 or MPPT2. So in this case, for the Tauro, because I believe we all know that we have 2 variants of the Tauro. We have the pre-combined and the direct. So taking the direct into consideration, you have them having all the MC4 plugs here. So you can now connect your respective strings to the MC4 terminals here. So if it is, so this is for direct variant of the Tauro. So if it is pre-combined, meaning that, okay, for example, if we have all these modules connected to one DC combiner box, and then all these modules connected to another DC combiner box, you can have something like this, where you have, because definitely if you're using DC combiner boxes, you're going to be coming out with a larger diameter cables. So here we'll now take this form, that is the input part of the inverter, the pre-combined version. We'll now have larger input terminals where you can now come in conveniently with your larger diameter cables. Okay, so as promised, we're going to be doing a short demo of the Solar.Creator and Configurator. So I provided the link here. So once you click on the link, it should take us to the landing page of the Fronius Solar.Creator. It's taking a bit of time, but I believe it should connect eventually. Oh, okay. So just have to skip the verification. So here we are in Solar.Creator. So once it loads up, we will now be able to do a brief demo on the Solar.Creator. For some reason, it's taking a bit of time, but here it is. So if you have an account, you can easily log in. If not, please continue as a guest. I think you would have the same access as those with the account have, just that you won't be able to save your projects. That's just the difference. So when you enter the guest via the guest link, you're going to see an icon or a hyperlink here saying quick PV design. So this is what the Solar.Configurator is now. So once you click on it, it's now going to take you to Solar.Configurator, as you can see. So we're just quickly going to enter the specifications. I already had one that we've all seen in the previous slide, so we'll just stick to it. So we're making use of this particular module. So for some reason, it's also taking some time to load. But let's go ahead and load the inverter. So so after selecting, let's try this again, because we'd have to specify the solar panels we're supposed to use. Yeah, another thing is to ensure that you have strong network connectivity or internet connectivity. I believe that's the challenge we're having here, probably the fault of the internet providers. Okay, let's see if we can make use of this. It's still giving us the same challenge. Okay, so basically, this is what I'm trying to bring our attention to. We're going to see different variants of how you can connect your panels to as a string to your inverter. So if, as you can see, we have the inverter ratio from 80 to 120. So if you want to maximize, as you can see in this case, it's 93% inverter ratio. So if you want to go to the highest inverter ratio, all you need to do is click on the arrow, double arrow. It will take you to the maximum possible design you can get per string. So for this particular default design, with the Fronius SIMO, you're going to have a possibility of connecting 5 strings to MPPT1. So each of the string will consist of 10 modules, and then we'll now have 2 strings, each comprising of 9 modules. So mind you, we already know that the SIMO has 3 MPPT, 3 terminals by MPPT. So the best option we can do in this case is to carry out to use string fuses. So if we look at this particular arrow here, or this arrow here, as you can see in this case, it's trying to get the explanation. You can see that string fuses will be required in this case. So if you don't want to use string fuses, you now have to look for a particular specification that doesn't require string fuses. So because of the fact that we're having challenges in imputing the particular module that we had in mind, so I'll just make use of this to explain what I mean. So for anyone you eventually choose, you can just click on it, and then you'll have all the information you need at your fingertip. As you can see, yes, that's confirming here that we require string fuses to ensure a good system design for this particular orientation. So that's for the Solar configurator. So now let's go back to Solar.Creator and then see if we can have a quick one before I hand over to Byron. So hopefully it loads without taking too much time. So I'm just taking a look at the questions. So please keep your questions coming. We'll be glad to attend to them during the webinar. Thank you. Okay, there we finally are. So we're now in Solar.Creator. So let's quickly see if we can start a project just to give us a clearer view of how it looks like. So we'll need to impute a name. So let's impute webinar, for example, and then click on next. So we'll now select what kind of solution we want to implement, if it's a residential or commercial, or a residential with a battery or commercial with a battery. So for time's sake, let's stick to commercial and then click on next. Here you'll need to impute the currency. I'm taking euro for neutrality. I prefer using the metric unit, and in terms of temperature, I prefer using the Celsius. If this is what you want to keep on using in your subsequent design, check this box. If not, you can just uncheck it and continue with clicking on start. Once you click on start, it will now take you to all the stages that you'll need to go through in terms of doing your system design. First off, you need to impute a location. So for location, I prefer using a map where I can just simply type in the location. So let me select one of our Fronius offices. I'll select this one in Paterberg. So if we choose that, it would now pop up with the solar irradiance, as you can see in this case, and then grid parameters, which you can, of course, make your choices from. Then once you've done that, you can click on next. Next up is it's going to provide information about consumption profile. So please select your load profile and then click on next. So next up is where we're going to do the roof planning. That is, if you're using a roof, or in fact, if you're using a free field, you can also do your design here. So if we select this, it will ask us to find a particular project location using the search bar. So I would want to make use of a particular patch here, with permission, of course. So in this case, it's asked us to find project location, which we have. So next up is to select the corners. So I'll select this point, another point here, one here, and then this edge here. So using this as the baseline. So once that is done, we can now, so since this is a free field, let's just select flat roof for the meantime. So it's of course going to take a flat surface orientation. So using this as the baseline. So when we click on next, we now have to impute a manufacturer. Hope we won't have any problem with it this time around. Okay, that's fine. So now we need to, so this is what we weren't able to do initially, to select the particular module. That is while we're using the Solar.Configurator. So in this case, I want to use a 400 watts module, as you can see. So once you make the selection of panels, it's going to bring out possible orientation of the panels. So I'm going to stick with the east-west orientation and then click on next. So we now save and exit. Once we click on save and exit, it's now going to take us to the next part of the design. So before it takes us there, we can see that we have the number of modules already projected. Okay, so we have our azimuth to be 293 for the azimuth to be 61 degrees for a particular panel, either facing due east or west, and then that of the other orientation, 241. And then the number of panels per array is 293 and 293, as you can see in each case. We'll have to note the tilt angle. Tilt angle for Hartenberg is 47 degrees. So we'll have to enter it in this case, 47 degrees. So yeah, so we now click on next. Oh, sorry, before we continue, please ensure that because it was a free field, so we're going to select freestanding orientation and not roof or building integrated. So let's now click on next. So if we click on next, it will now take us to where we're going to size the inverter. So I'll go for 120% inverter ratio. So once you select any inverter ratio, and then of course select your minimum and maximum module temperature, it's going to come up with a selection of inverters to be implemented for this purpose. So to keep our options narrow, I'm going to stick with the SIMO 20. So you can deselect the other ones. For your individual configuration, you can of course tick any one you want. The more inverters you select, the more options you're going to have. So let's stick with the SIMO 20. As you can see, it's the only one I have selected. And then we can now go ahead and show calculation. Once you click on show calculation, it's now going to bring up the possible combinations of inverters that are going to be used to configure the system. So in this case, there could be a problem with the inverter ratio. So basically what we're going to do is to reduce it to 110. So let's leave it at, okay, probably it didn't record the 120. So let's try this again and see if it works. If not, then we'll have to adjust the inverter ratio. So these are basically what we'll need to note so that the system would properly aggregate and do the system calculation for us. So that's it. So here we're going to see a suggestion or a recommendation of making use of 10 inverters to implement this particular project. Then we're going to have a breakdown of how these inverters are going to be connected. Further down, you can see that we have other results. We have up to 10 results. So the first one is usually the one that is recommended. If you want to use other inverters, you can of course select other inverters, like the Tauro, for example. So if you choose the Tauro, which have higher capacities, you're going to have lesser number of inverters to be used to implement this particular project. We're targeting looking at a PV generator capacity of 234.40 kilowatts peak. So for this, it tells us that we're going to use 10 inverters. All of them are SIMO 20s with respective kilowatts peak generated per orientation. So for this, it tells us that we're going to have two setups like this, SIMO 20s. Now for one of the inverter, we're going to have 3 strings of 12 modules and then connected to MPPT1 and then 2 strings of 11 modules connected to MPPT2. So this would now be multiplied by 2 to give you the capacity generated by this set of SIMOs. Same applies to all the other system orientation. By the time you sum all the power generated, it's going to amount to 234.4 kilowatts. So that's basically how you can design a system using Fronius tools, especially the Fronius Solar.Creator or the Fronius Solar.Configurator. With the Solar.Configurator, you can use it to design the number of strings to be connected to the inverter. With the Solar.Creator, you would use it to design the entire system comprising of several inverters. So in this case, we're going to need a smart meter at the primary feeding point. I'm going to go with 1 unit of the 5 kilowatt type. And then we're now going to have to impute electricity cost. This is just to give us a perspective of what the system is going to yield. It's approximately 0.25, I believe, if I'm not mistaken. And then feeding is usually around 0.05. So let's put this at 10 years calculation. Let's leave this at the same 10 years calculation. And then once you impute all this data, well, this is just for example, of course. So if you have the exact values for your particular region, you can, of course, impute them, and then the system, the software will basically do the calculation and then give you the result. Yeah, so that's pretty much it. Because of want of time, I would have to stop here so that Byron can continue with the rest of the presentation. So, but basically, after the result is calculated, you can now have a report that tells you all the information about the system, and then, of course, information about the return on investment. Good. So, yeah, this brings me, like I said earlier, to the end of my part of the presentation, to quite a while. So, Byron, if you please, you can continue from this point. Thank you.
Thanks, Brian. So next we'll be covering the system design with the Fronius Taro configurators. So the versions of the Taro inverters. So you got the Eco variant. So the Taro Eco D. So the D is for the direct DC connection. So this is when the inverter has MC4 connection plugs underneath the inverter, 14 connections for the 50 kilowatt variant, and 22 string inputs for the 199 kilowatt variant. So this allows you to do string monitoring, and also string fuses as option is integrated into the inverter. Then you get the Taro Eco P. So the P is for the pre-combined connection. So this allows you to have DC inputs 3 times. So you can have positive and negative 3 times. Up to 90 millimeter squared cables is allowed. And these are connected via V clamps inside of the inverter. So for the D, or decentralized topology, so this is when all inverters in the system are placed near the PV modules, so as in a typical PV system design. This allows for longer AC runs, but also shorter DC runs. Therefore, additional AC combiners and differing cable diameters are necessary, especially with your losses that will occur from the extended length. So that is one of the limitations with your decentralized topologies. With the centralized topology, so this is the P variant, the pre-combined. So this is when the inverters of the system are placed near the feeding point, so primarily near your AC connection point. What this entails is longer DC cabling, and also this will entail additional DC connection boxes and connection sets, as you'll then experience greater losses on the DC side because of the cable length. So that's why it is required that you use the pre-combined topology in order to achieve that system design. With the Taro inverters, it is also possible to do AC daisy chaining. So this is a special AC connection area in the inverter that's then possible to connect multi-inverters together on the AC side. So for example, you can connect 2 by the 100 kilowatt variant of the Taro Eco together, or 4 by the 50 Taro Eco variant inverters. So this is your conventional installation. So this is when you'll have your inverters followed by an AC cable running to your PVDB, for example. From each inverter, you'll have its own separate AC connection cable. Whereas with the AC daisy chaining, you will then have simply one cable connecting one inverter to the other, and then having one master cable effectively running from your master inverter all the way to your PVDB, for example. So this allows you to reduce cable costs as less AC cable is required. So it's one of the freedoms in the design of the Fronius Taro inverters. Next topic is system construction or layout. So on a typical system layout or SLD, you'll have main components. So you'll have your PV array, which is your racking system and lightning protection, followed by your DC cabling. So this will be your DC combiner boxes if necessary, or surge protection, which is always advised, as well as your inverters, and then followed by your AC cabling. So this is AC combiner boxes if necessary, also surge protection, and then obviously on your metering side. So you'll obviously have your main grid meter, and then followed by a Fronius smart meter. So this is what an actual system layout would typically look like. So here you can see your Fronius inverters, followed by their separate PV arrays that are then connected to the inverters, and then followed by their AC connections into the PVDB, for example. You'll then have one master cable running from each PVDB to its LT panel, where it's effectively tying in, as well as its main breaker for each separate individual PVDB that's being fed into the system. So here you can also see is the energy meter that's helping to monitor exactly what flow of energy is occurring. Another important thing to note is here you can see on the communication side. So here in this system, it's got a genset integration. So it's using a DIVE controller. So here it's using obviously a display unit for the DIVE, and then obviously the communications. So it's using Modbus RTU, for example, from the controller itself, then communicating to each inverter via Modbus RTU. So it's RS485. Whereas the TCP connection is then from the DIVE to its separate controllers in itself, and also the CAN bus. So this is just a typical example of an SLD that will each be required at each individual site. Installation hints. So this is the next for PV array and racking system. So modules are typically roof mounted for residential or C&I projects. So it's built special built structures. So also to be aware of mounting recommendations for the module from the manufacturer. So normally they'll give specifications of a clamping zone. So this is also to help with shading effects, and especially for tilted modules need to be addressed. All structures must be able to withstand both uplift and downward forces. So for example, wind and snow in Europe, for example, or areas where snow does occur. And then obviously high wind areas, obviously for the uplift of modules. For roof mounted modules, sealing of all penetration points must be done to obviously ensure that no water leakage can occur, and an appropriate use of interconnectors as well as tools must be observed. So most modules are supplied already with MC4 connectors on the positive and negative side, and the modules and strings interconnections have a huge impact on the DC power delivered to the inverter. So if you've got a faulty connection plug, for example, you'll see a derate of that string, for example, or a certain error, isolation error would occur if a DC connector, MC4 connector, apologies, is not connected properly. On the DC cabling side, so always to ensure all cables are correctly sized and current expected. Avoid common cabling mistakes. So this can be unconnected strings. So it can be hard to identify with central inverters or large strings. So if you've got, let's say, 10 inverters in each having 22, it's going to be very difficult to find 220 strings, for example, to try and manage that. So it's just always just to avoid unconnected strings, because to try and fault find is going to be very difficult. Reverse string cables can eventually damage the inverter. The problem can be overcome by clear wiring labeling. So this will also help you to identify fault finding. So if you've got a string that is faulty, this will also help you to identify the positive and negative of each string. Swap strings, it can happen that the plus and negative of relevant or related strings are mismatched or matched. Becomes very difficult to trace on big systems. Possible in this case to use wrong series or parallel string connected to the inverter may also result in damage to that inverter. Regarding connectors itself, so this can also affect is poor crimping, for example, so using of wrong tools. So if you're using a pliers to crimp instead of the actual tool that's provided for the MC4 connectors, this can cause overheating. Also, what's damaging is connectors that are exposed to moisture before they are connected. That's why it's always, if you notice on some inverters, you'll see there's a rubber stopper that is provided on the positive and negative side. This is just to help prevent any moisture from buildup inside that connector before you are establishing your string inputs. Another important note is connectors not latched can cause arcing over time. So the MC4 has a specific click that it slides into. So if it is not clicked, for example, this will then cause that arcing effect to then occur. High resistance on the DC side, so the voltage may seem okay, but until the inverter draws current, this will then cause a voltage drop and the inverter will shut down. So it can be caused by damage or manufacturing defects in the solar panels. Overall, ensure cabling is neatly done. Use cable trays as needed and sufficient labeling to help with your DC cabling. So the inverter DC connections. So again, the cables you can have is 2.5 millimeters squared to 16 mil squared. Copper or aluminium cables is possible. So on the SIMO, 2 or 3 strings per MPPT tracker, or on the eco inverters, where it's 6 strings, but it's 1 MPPT. So it's string fused integrated. You'll then be provided with a DC connector kit 35. So this is allowing for cables up to 35 millimeters squared. Important note is to always still use the strain relief on the inverters, as well as on the old snap inverters. You would notice the old string inputs if you are doing direct. But if you're doing pre-combined, you are allowed to drill out this section and then to simply fit a gland for the cable that you're doing for the pre-combined. So on the string connection point, so here you'll have your one array, so PV1, so you've got your positive and negative. So you'll have it on input 1 and input 1 on the SIMO S. So this is for single string. Whereas for the next example, so you've got PV array 1 and PV array 2, and they going to a PV junction box. So you'll obviously have one cable positive and one cable negative running from your pre-combined junction box. If it is a SIMO M, so a multi-string, multi-MPPT input inverter, so it's 2 MPPTs, you'll always have to make sure that the MPPT tracker is off, as they're all sharing now effectively a common bus bar in a sense. Whereas for the SIMO N, this is another example. So if you got PV array 1 and PV array 2, so you got your positive and negative from each array, you'll then have input 1 on DC on your positive side, and obviously DC 2 on the positive side also. So this is due to the positive side having a separate bus bar on the multi-string design, but on the neutral side, they all share a common neutral. So it doesn't make that much of a difference, for example. So if you've got, let's say, 3 and 4, and let's say 3 and 4 is only on DC2, they'll all the same orientation as PV2, they will then occupy 2 and 3, for example. Another important note is when you are pre-combining and you don't have the DC disconnect kit, you will then be able to use a jumper cable. So this is when you are simply then doing a connection from, apologies, from your DC1 positive and obviously your DC negative, but you'll have a jumper lead from 1 till 2, just to act. So you're effectively achieving the same principle as your DC disconnect in a sense, and also to ensure that your MPPT tracker 2 is off when doing any pre-combined systems. On the overvoltage protection side, so your overvoltage can be installed on the DIN rail space provided in the inverters itself on the right hand side. So type 1 or type 2 or both is provided. So the S or M version, so 1 per MPPT. So you'll have on the positive and negative side can be directly connected to the screw terminals. So normally inputs at the top of the screw terminals, and then your earth potential from AC termination or external will then be connected. And then obviously the signaling output to the Reservo card for monitoring. So this is that cable that is provided with the surge protection kit, which will have to be plugged into the Reservo board underneath. On the AC cabling side, so obviously to ensure all cables are correctly sized for the current expected. So possible concerns with AC cabling, so grounding problems. So you use materials that may have different galvanic properties. So example, if you're using a copper cable and aluminium, if a painted metal part requires grounding, scrape the paint off or use paint cutting fasteners. A proper earth rod is required to ensure maximum or minimum grounding requirements are met. Another important note is the high resistance. So the grid voltage seems okay when measured, but inverter trips when power is exported. So the high resistance cause the voltage to rise, tripping the inverter, or high resistance can be caused by loose connections. Also, another thing that can occur is your AC breaker problems. So always select the right breaker for the system current. Breaker failure, either open or closed, can be high risk factors. Always test before proceeding. So always test your breakers and everything before proceeding with your connections. Another important note is your cable terminations when they are too big or too many. So always ensure that the right torque is applied with your connections. Be careful with straight cables, as a strand can arc over the next cable, for example. So if you're putting on a lug, for example, and you've got a cable strand that's come off or is slightly out, that can cause an arc over time. Another important note is over time, all cables loosen up, and that's why do retorquing after a certain period. So obviously the cables heat up and cool down, and this causes those connections to sometimes get a bit looser. The next point is on the inverter side. So on the inverters, observe cleaning all installation recommendations. So mounting must be carried by a full weight of the inverter. So always make sure that the structure is able to carry the weight of the inverter itself and it's not unstable. Spacing, so this is important for servicing as well as air circulation limits on the inverters. So a lot of the inverters push the heat out from the top. So that's why it's always important to note your height above the inverter is not obstructed by anything like a roof, for example, or any other obstacle. An important note is always no direct sunlight to avoid any case of derating. Otherwise, if you are using the Taro, for example, which is designed for direct sunlight installations, then it is possible. And then obviously the Fronius recommendations of location choice. So always to have a covering over the inverter. Even though the inverter is IP rated, it is always important just to cover it in case. Not exposed to direct sunlight, and then obviously to always oblige to the limitations on altitude for voltages. With the inverters for inverter communications, so in case more than one inverter is used in a system, inverter-inverter communication must be clear. So this is when you're using Fronius Solar Net Ring. Other mechanisms for plant control can also be used. Failure in the communication loop can cripple the entire system. So if you've got a master, for example, and one of the slaves is failed, the master will also be limited because there's no communication achieved by the slave inverter. Most failures in operation caused by communication hiccups. So if there is a cable that is accidentally being cut, for example, in the snap inverter series, always is important is the missing termination plugs. So the RJ45 connection end of line plugs. If they are missing, the loop will not be closed, and that would cause a failure in the loop and again crippling the entire system. So using the RJ45 sockets or plugs Ethernet cables, the solar net ring can be extended to 1,000 meters. So this is due to the limitations of the cable. So you can have one master followed by 9 slaves. So you can have 100 meters between each inverter. So that gives you a total limitation of to be extended to 1,000 meters in total. On the metering side, so a typical system will have at least 2 meters. So always a grid meter that's provided by your grid operator, as well as a Fronius smart meter is always needed. So this is to help with achieve zero feed-in limitation or the feed-in limitation if necessary. So it allows determination of the system's profitability by comparing the production and the consumption side. Communication between the smart meter and data manager must be established. So possible errors, so missing terminator resistance at the smart meter or the data manager, using of the wrong cable type. So always use twisted pair Cat5 cable. So 3 twisted pairs. So you'll have one for your positive, negative, and for ground. Screwing Modbus cable together. So insulation at the meter or data manager, and do not interchange the parts. It will then give you no communication. So for the smart meter connections, so here's where you'll have your CT connections, the inputs. This will be your 120 ohm terminator resistor, which is always important. And then obviously on the Modbus switch, you can enable that 120 ohm resistor also on the data manager or pilot device. Again, important note is your shield, your positive and negative signal. Always use the twisted pairs. And then for some of the smart meters, they will require an additional input to be able to switch on. So it'll be either line 1 and neutral, for example. Whereas the older units, they didn't require that. So it's just an important note on the smart meters. For the smart meter settings, so on the 100 amp single phase and 65 amp 3 phase, only the address has to be set. So on the 5 kA 3 phase, it is required to correctly set the transformer ratio on the current transformers, and then obviously your voltage transformers. Changing the transformer ratios will reset the smart meters counter. So if you are, let's say, have a smart meter on site, and you've left for a month, and you now come back to change the CT ratios, you will then lose what the current counter has acquired during that month that the system has been running. With the master password 9753, it is possible to reset the password of the smart meter to the IME standard password of 1000. Selection criteria for your current sensors. So obviously on your primary current, so maximum current per phase, the current converted with a primary current greater than the maximum expected current per phase should be selected. So it's always important is that the closer the expected current is to the value, the more precise the measurement will be. So also on the power side, so the smart meter needs 0.3 VA to carry out its own measurements. Losses can also occur on the outgoing and returning leads. The power of the current converter must be greater than the sum total of the power of the Fronius smart meter and the leads. The higher the power, the better. So for example, if you've got an outgoing and returning lead between the Fronius smart meter and your current converter, together to by 0.5 meters, so it's 1 meter length of copper cable of cross section of 1.5. So that means it would be 1 by 0.6 VA. So then the self-consumption is 0.3. So your total sum is 0.9. So you are, or higher is suitable. On the commissioning and monitoring side, so you'll have your system communication, your commissioning. So all inverters becomes the control, so operation command center. So all systems malfunctioning may in error be associated with the inverter. The inverter will most of the time send alarms or error messages, either displayed on the Reservo screen or sent via email or displayed on SolarWeb itself. It could be an inherent inverter error or another component within the system that has occurred. Ensure all installation recommendations are thoroughly followed. Make the commissioning process easy and smooth. Checklist for critical areas and require before. And then obviously commissioning throughout relevant inverter web user interface. So for the Snap Inverter, Taro, and Gen 24 Plus. So on the system monitoring, this allows for operation and maintenance. So on the monitoring portal, should have over 99% availability, and any planned maintenance schedules on the portal must be communicated regularly. Monitoring portal should be API compatible, which it is, and all attributes of Fronius SolarWeb. System data communication, so the owner information, so names, location, and contact information, so email and phone numbers. You also have the system information, so design module, normal power, your installed DC capacity, module manufacturer and module quantity, inverter manufacturer, module and quantity, your racking system, so specs on modules, model and quantity. This allows for operation and maintenance. As built photos, so this is just an example. You'll have a photo of your PV array, the inverters, cabling, your switchgear, etc. For any further information, recordings are available on our homepage, so operating and installation instructions, or on our YouTube channel under the how-to installation videos. Webinar recordings are also available, as well as our Sub-Sahara Africa playlist. Your Fronius Solar Energy team, so this is for any technical questions. It's pvsupport@fronius.com. For any trainings, pvtrainings@fronius.com. For sales international, any after-sales services. And if you are wanting to get in contact with our TSAs directly, you can contact Cyprian for the Western African region, myself for the Southern African, and David for the Eastern African region.
Yes, indeed. I must say a very big thank you to all of you that have taken the time to attend this webinar. This is where we come to the end of today's webinar. And we sure hope that we gave you a pretty good dose of information that you want about proper PV system design using Fronius inverters. So until we come your way again next time, we're going to say Thank you for attending once again and enjoy the rest of the day. But before we go, we shall take some time to answer all the questions on the chat. And then once we're done with that, we shall now call it a day. So thanks once again and bye.